Hi, friends. Welcome again to another episode of Beyond the Clouds Edge to Edge Transformation. This transformation is global, it's affecting every area of technology. There are so many emerging technologies and awareness in people's minds that this technology can do something for them. Some of us are excited, some of us are worried. But no matter what, nobody can be completely neutral in this environment. And here with us today is Claire. Claire has had an amazing career. Claire, tell us about your story. How did you become the Claire Vishik we know today?
Accidentally, just like probably many people in the same environment that I am in today. When I started out coming from a family of academics and marrying another academic very early, and he is 6 years older than me, I thought I will be an academic as well, just like everyone else in my family. But the logistics, the family, we had a child fairly early. Other considerations played a role. At some point when I was in graduate school, my husband decided to take a job in Austin, Texas. And that was the start of my story. When we transferred here, the academic environment is different in that there are fewer universities than in Chicago, where we came from. And suddenly the practical issues industry became more attractive. I took an internship at Schlumberger Laboratory for Computer Science almost as soon as I arrived. This laboratory was a pioneer in both artificial intelligence and internet services that were in the 1990s really in their initial stage. The commercial internet certainly was popular. It has started, but it has not been validated with everything that we know now, state of the art, technologies, infrastructure, standards, research in the right direction. So I started in the lab, and in one of the projects that I had there, I had the chance to test my interest in emerging technologies, startups in general, and aspects of internet technologies that have not been reliably addressed at that point. One of the projects I had was commercializing or attempting to commercialize an application that was developed by researchers at Dartmouth. It was an agent-based application, well, sounding very modern and actually very modern in its nature. It delivered customized news to subscribers via a variety of sources, including satellite, using all kinds of search engines that were available at the time, including experimental. And working on the system, I noticed that a lot of things were missing. One was infrastructure, the other one was security. The third one was reliable approaches to privacy. The fourth one was personalization, and so on and so forth. This set me up on several directions in my career, including security and privacy, including interest in infrastructure, and including the understanding that everything is interconnected in the digital environment. It's not reliable, not productive focusing on one thing, say a small tidbit in software or a cryptographic algorithm, because the impact of something like that will be important but limited. That's how I gradually became a generalist, but in a good way.
That is amazing. I like what you just said. Everything is interconnected in the whole world, and definitely in the world of technology, we are seeing that. So you are there in the pioneering days of the commercialization of the internet, and some of the issues at that time, whether it was cybersecurity, privacy, safety, ethics, which, if you remember, in the 80s, we even had this huge virus, which our teenagers started, and it brought down half of the internet. So a lot of those issues keep coming back. And what is the reason for that?
I don't think they are resurfacing in the same way because the infrastructure is definitely changing. My career was very favorable from this point of view. At some point, I started out in the Laboratory for Computer Science, that was a pioneer in internet technologies. That was software. Then I moved to AT&T Labs, and that was networks. After that, I moved to Intel. So that's a combination of everything, but predominantly hardware and components. Understanding the whole picture tells you that, the same questions remain, but they don't remain immutable. They come in different ways. If you look at technologies that we knew about back then, and I'll start with the positive, not negative, like privacy, security attacks. A lot of technologies we knew about back then. The artificial intelligence certainly started, I would say, in the 1950s conceptually, 1960s practically. And the rule-based expert systems that we were building at my first lab in Schlumberger Laboratory for computer science were certainly viable. They did things similar to what we are doing now. They used approaches that are still used, like ontologies. Only it took forever to create those systems. Everything was manual. The assumption at the time was that you need to understand and replicate the human brain, how the brain works. So there were endless projects. For instance, a project that tried to read and understand the children's encyclopedia. It took 20 years. It was located in Austin. But there was an ontological search project in Fosluz that took many, many years. Everything to create support for this project was manual. The ideas was correct, but what we learned eventually, in order to imitate the human brain, you don't really need to work in the same way. Instead of semantics, you could use syntax. You could look at things that computers do better than humans, the ability to process a lot more information in a different way, the ability to count faster, the ability to understand, find, and process minute differences in pictures, for instance, and so on and so forth. And based on this formal compare and simple data processing, we now have modern artificial intelligence. It does the same things that we did in the 1990s in my lab, only it does it better, based on completely different principles. That's how it works in general. Another example that talks a little bit about other technologies, back in the day, when I started working in that lab and then AT&T labs, one of my projects was software-defined radio. This is something that allows to change spectrum, frequency, and bandwidth in software. This problem was well understood 30 years ago, but it wasn't really commercializable because this activity is resource intensive, and we did not have significant computing power and battery power in the miniaturized devices that could support it. So we could do all this. And then gradually the situation changed. At some point, we were able to statically switch bands. Remember those telephones where you would come to Japan and you would switch to a different band? It would be painful, it would be slow, it would be very expensive, but it sort of worked. Now you don't notice when you travel. You have those devices in the cars everywhere on your telephone that use different bandwidths, use different frequencies to operate all kinds of devices. It works seamlessly, but not because of the core technology. It works seamlessly because of the supporting technologies, computational power, ability to miniaturize, ability to improve batteries, and so on. And yet another example that probably will appeal to researchers among the audience, there is a technology that is more than 30 years old, PAFs, physically unclonable functions. It uses imperfections or actually minute differences in hardware, ICs specifically, in order to provide primitives for situations and security applications. This technology was simulated for 20-25 years in FPGA, and it appeared very promising. It is still promising, but in a different way. At some point, about 15 years ago, we got funding from the European Commission to implement various types of PAFs, physically unclonable functions, in silicon. And then we tested those devices. And during testing, we discovered that the expectations about their behavior were different from reality. Simulations are really good, but they are not perfect. Now, there are some companies that use these technologies very successfully. One of them is Intrinsic ID. That company was a participant in that European funded project back in the day. But the whole view of the field is different because we understand it in depth. So when you say the same problems come up again and again, they do, but at a completely different wavelengths.
Yeah, it's almost like relationships, right? The same problems come up, but in much more complex ways. The nuances are very different. Which reminds me, there was this famous book called 1984 but it was predicted that machines will take over the world. That didn't happen. We took over machines and became more productive with a few hundred neurons, maybe a few thousand neurons. And now we are at a trillion neurons. The same fears are coming back that machines will take us over and we'll have artificial general intelligence. What's your prediction? Do you think we're close to AGI, artificial general intelligence?
As I said before, machines operate completely differently from humans. They can emulate human brains. They do some things much, much better. Computational problems, for instance, they do other problems much worse. For instance, in extreme examples, they are improving. It is a promising field, but certainly not nearly equivalent to what the humans can do. Even simple equation solving, for instance, PDE solvers based on artificial intelligence, don't understand some equations. So there are areas where machines are much better. There are areas where machines are much worse. There are some areas, however, where the behavior of the machines is dangerous. A lot has been said about transparency and explainability, but artificial intelligence, machine learning based applications, as they learn, generate additional code automatically. It's very difficult to create true explainability in systems like that. It is not as easy as transparent as it was in the older generation rules-based systems, because there you have the rules, it's immediately clear how you arrived at your conclusion. Especially in highly computational applications, but also in highly semantic applications where you would discard certain statements as wrong just because the developers decided to do this. It's very difficult to create true explainability. In this fashion, while not replacing humans, modern machines certainly have an outsized influence on how problems are solved. This influence is sometimes benign because they make things faster, but it could also be not benign when automatically generated code based on some misguided or deliberately introduced signals create wrong answers that could impact safety, that could impact understanding of a problem, understanding of trends, and so on. So I think we are in a situation where things can get dangerous, but not in a way that you indicated at first, at least not yet.
Not yet. You talked about software-defined radios. We had ham radios, we had software-defined radios. Today we have software-defined vehicles. We have software-defined networks. Audi is claiming to have a software-defined factory. What's next in terms of automation where software can be used to take charge of and give you the flexibility to use real-life objects?
Yeah, that's another interesting problem in how it developed. Intelligent networks have been talked about for generations. Certainly, I have come to the lab as a young undergraduate to hear about this many years ago. But it is also true that intelligent networks did not begin to appear until very, very recently. In the past, the network is very simple, really dumb. The edge would be reasonably intelligent. So today, we have a situation where in 5G and in the future in 6G environments, the edge and the endpoints become much more capable of operating intelligently and influencing the core network. So today, I think, is the first instance where we truly have something approaching the vision of the intelligence network, and we need to evaluate it from this point of view. Similarly to intelligent factories, there were computerized conveyor lines, production lines for many, many, many years. Robotics have been used in precision situations for a long time. This is not new, but a data-driven, completely electronically operated factory, we are very far away from this. There have to be humans at the helm, still making decisions, monitoring, understanding what may go wrong for a variety of reasons. There are technologies that are looking into this to create a true difference. of course, intelligent manufacturing, but also the use of digital twins that replicate the production lines and allow to operate them entirely from software, and therefore eventually at some point from artificial intelligence. There are data-driven factories in all areas, and in fact, modern manufacturing would not have been possible without data-driven factories and manufacturing. But a completely software-defined, software-operated manufacturing, we are not yet there.
We have plenty of things to do. It's not the end of the rope. We researchers and people have lots of good things to do. That's good to know. You've said something very interesting. You said about imperfections in hardware can be used for security applications. Can you give us some details?
I misspoke there. I said tiny differences.
Tiny differences.
Yes, clarification. ICs are all approximately the same. Hardware products that focus on memory are all approximately the same. But there are tiny, tiny differences that allow differentiate between each part. When each part has its own identifier through physically unclonable function, identifier that's already embedded, that cannot be changed. That creates an additional opportunity to identify the part and track it through its lifetime if it is desirable, or simply make its delivery to the customer more efficient. It's like your ID. You create your username and password, and that's a way to identify you if you wish it to track you, to deliver personalized content to you, and so on. In this case, it's more akin of biometrics. It's already embedded. It's unchangeable. And that's useful in some situations to take advantage of and to treat as a security primitive.
Wow. Just like biometrics can uniquely identify humans, there are equivalent biomarkers, if you will, of slight differences in the hardware, software, and the physical component that gives a unique signature. So you can use it for tracing, tracking. Is that right?
Yeah, in physical components based on paths-related art or based on dye, slight differences. So it's very similar to DNA. It's not the same. DNA, for one thing, is extremely complex. You can use those procedures similarly to using an embedded key to identify a device.
Wow. Now, you've worked on all kinds of technologies from the early days of the internet to where we are today. What is it that you're most excited about among emerging technologies?
There is a lot that I'm excited about. Among those technologies that are promising, I can mention quantum materials, two-dimensional materials that have specific properties. I can mention things like high-temperature superconductivity. If ever it becomes commercialized, it will certainly change the world. I can mention in the hardware area advances in batteries, the use of photonics in a variety of areas. Now it's still expensive, but for some areas of operations like artificial intelligence that is highly parallelized, it will be very, very important. Approaches that are completely novel always excite me, whether or not I can participate directly in the creation of new technologies. An area that comes to mind, for instance, is approximate computing in security. Approximate computing has always played a large role in areas like artificial intelligence, where you focus on identifying what is easy to identify 80% of the cases, and sort of ignore the rare cases in situations where it's not important. But in security, you typically have to be precise. You have to identify an issue, a device, a software component, a user correctly. You have to implement encryption and authentication correctly. Yet models have appeared that are based on approximation, approximate security, approximate cryptography. This is very promising. It could give us new ideas on how to deal with the resource intensity in security applications. Indeed, in many situations where cryptography is at play, a component or a software package may spend 40% of the cycles just encrypting and decrypting. That is a huge overhead. Approximate security offers a way to think about this area that is less resource intensive, more sustainable. Whether or not it will be commercialized, I don't know. But generally, you look at an area of technology, an area of science, You find new ideas, new approaches, and you transfer them into something new. Maybe the original area will never be commercial, or if it becomes commercial, it will never make a significant impact on the environment. But subsequent areas certainly will. This is how it works.
Yeah, through my career, I've seen that no good ideas ever got wasted, but they may not have been used the same way as it was invented. One of the interesting things I found about the semiconductor base, which now we call the siliconomy, is that it has gone in leaps and bounds using the technology it has created in the previous generation, right? AI algorithms, hardware gave rise to better hardware and then better software. Do you see similar things happening with the latest generation of AI?
The ability to quickly process data impacts all areas. You were talking about the factory floor, and certainly not just in semiconductors, everywhere. Artificial intelligence is used to analyze not noticeable otherwise issues on the factory floor. Similarly, an example that comes to mind is building integrity. Remember that condominium in Florida that collapsed, killing a lot of people. For something like that, the ability to take pictures with considerable frequency over a long period of time and look at minute differences among those pictures will certainly give you a signal that something is not right, probably decades before a building is about to collapse. So there is the reverse relationship, though. Today's artificial intelligence processing so much data so quickly would not have been possible without advances in computational power. Computing power is really the foundation of the ability of the humankind to do artificial intelligence. 20 years ago, with the same algorithms, the same understanding of how to do it. But without advances in storage, computational power, networks, software approaches, it would not have been possible to do what we are doing now. Nothing, and I mean nothing, including the keys you are using to enter your car, would work without semiconductors today. Artificial intelligence is a logical development of making computation more powerful, and that's entirely based on semiconductors. The way forward will be determined by where the technology environment in disruptive technologies are going. It's a two-way street. One influences the other constantly.
There was a time when you and I could go to work, do our work, then come home and don't have to worry about work. But today, we cannot say that. Everywhere we are connected. How can we find work-life balance if we are always on all the time? There's an expectation from customers saying, you told us you'll get it done. How can we find that balance?
Honestly, I don't see a lot of difference. It's easier to do certain work without needing physical proximity to servers and specific devices just in your home office. But looking at my parents, who were both professors, they work very long hours. They worked over the weekend because they liked what they were doing. At the time, there was nothing but the telephones. What I think we have lost is true collaboration. Even at the beginning of my career in the mid 1990s, there was a lot more face-to-face contact with my collaborators. Now I have some collaborators that I have never met in real life, only online. I am sure it's true for you as well. The subtle difference that you get when you are working on a complex problem and you are in the room together. You could write on the blackboard. You could watch the reactions of your collaborators. You could understand immediately what they understood, what they found, and not so convincing that has been lost. It has nothing to do with the work-life balance. Work-life balance is a decision that we all make for ourselves. I heard and observed also that the latest Generation Z, is much better at that. They set out to have a life outside of their job and they stick to it. But for my generation and the generations before and the generation after, working very hard when you like your job has not changed. Certainly has not changed because of the technology.
You're absolutely right. Even though we didn't have computers at home or in remote places, we carried the problems in our head. And I remember getting the solutions at the weirdest possible places. So the always on culture is a personal decision rather than the availability of resources. I think you're right.
What also changed is the distribution of your tasks. I remember how my parents would write mathematical formulas in their papers by hand. They would get a printout with the text printed, and then they would very carefully enter the mathematics in there because back in the day, there were no programs that would help you do this. And it certainly took a lot of time. Now there's a lot of time that we spend on other things. For instance, looking at much larger number of papers than we did before because they are all available online and not just in one library where you go. And they are all connected by their topic. You would not think of looking at this area if you went to a traditional library before there were electronic catalogs that incorporated full text. Technologists are doing different things than 60 years ago. But the time they spend on the work they like is probably the same.
You have worked in so many different areas, geographically, in terms of sectors you worked on, technologies. What did you enjoy the most? Or was there any aspect of your work that you enjoyed the most?
If I had to select one, I would probably talk about mentoring. The thing I am proud of the most is the success of my mentees. It's incredibly refreshing to teach a person everything, how to write a paper, how to do research, what errors he or she is making in their reasoning, and then see them rise to the top, creating new technologies, becoming notable professors, becoming CEOs, changing the world. Other things that I like, and they were present in all my jobs, is challenges. It's sort of boring to do the same thing day in, day out, and make sure it's perfect. It's needed. It's necessary in technology. What appeals to me is to see a problem that does not seem to have a solution. Look at it from various different points of view, alone or with collaborators, and find a way to make it work. The joy of getting something to work, which used to be completely impossible in the technology area, is certainly great. Not as great as seeing the success of my mentees, but significant. So those are two top things: solving difficult problems, number two, and training the new generation, number one.
That's wonderful. And I think there will be ample opportunities as long as we're alive to do that. When we go through any kind of an adventure or any amount of work for an extended period of time, it changes who we are. It transforms us. Are you the same Claire who joined the industry and the academia, or have you transformed?
I don't think people change fundamentally. They change superficially. They become more self-assured, more polished. They know how to answer certain questions. They know how to deal with certain challenges. They know what not to approach. This wisdom comes from experience, and it certainly affects how people come across when you meet them. The fundamental foundation is probably the same for everyone as it was when they started, when they embarked in their career. I am still the same Claire that I was at 18. I still like the people, trying to understand them. I am still idealistic. I am, like actually most of my colleagues, an introvert, although I thought to be an extrovert when needed. I am still devoted to my family. I still value friendships. I still like classical music to listen to and to play. I think what you gain in experience changes you, but only superficially.
You said you love mentoring. Now that Gen Z is here and many more generations to follow, and the pace of technological change seems to be faster than when we started, or at least the manifestations are more varied. What advice do you have? How should people approach their careers?
They should approach their careers in ways similar to what successful people did before. Learn the basics. There is no way around it. Well, there are exceptions, but they are just that, exceptions. You cannot become a good engineer without having a basic knowledge of science, of mathematics, and surrounding issues. You need to work hard. There is no substitute for expertise, although you can use today ChatGPT or other models to answer questions decently and analyze the space where you work with reasonably accurate answers. There is no substitute for becoming an expert. What do people say that you need to spend at least 10,000 hours to become an expert in a field? And this is still the case. You cannot become an expert by asking questions of ChatGPT. This will not put you on the road to developing new technologies, understanding what is missing, understanding how to solve difficult problems. I would advise the people who enter the technology field today, be a good student, work hard. It will definitely pay off. Be sure of yourself. People make mistakes, but that doesn't make them any less of an expert if they work hard on it. Look at people around you, the ability to work with people, the ability to understand them, support them, the ability to find mentors, and then give it forward to your own mentees. Make sure you have a life, support your family and your friends beyond your job. And as the Constitution of the United States says, don't forget about the pursuit of happiness. It's always important.
Well, such a joy talking to you, Claire.
Thank you very much for inviting me. It was a fascinating discussion that made me re-examine some of the things I have not thought about either ever or for many years. It's great that you are doing this work, that you are interviewing different people to get different points of view and find what links the technology community together, how we are similar while being so different in our approaches to delivering innovation. So please keep up the good work and looking forward to talking with you again if the opportunity arises.
Thank you, Claire, for giving my closing statement. When I started, I thought I was exploring all facets of technology. The more I get into it, we're exploring the human dimensions, how we are all interconnected, and who are the people and what are they up to. It's not machines creating machines, but humans engineering things and making it happen. So thanks again. And to everybody listening out there, I want to hear from you. We want to know what interests you. What are the challenges you're facing? Thanks again, Claire, and I look forward to meeting you.